Hey everybody, Dr. D here, and what we are going to do today is I am going to go over how to use MATLAB to graphically plot a pendulum in motion. Now if you're watching this, you will already have completed Lab 1 in ESG 455, and this will kind of serve as a way of bridging what we did in the lab and what we're doing in class, hopefully. So if you have any questions, leave them in the comments below, or email, come to office hours, do whatever it is you need to do. All right? Great, let's get started. All right, everybody. So what we're going to be doing is we're going to open up MATLAB. You can see that my MATLAB window is currently open. Okay, and so the first thing that we need to do in MATLAB is derive the equation of motion. Okay, now presumably we've done that, right? But just so we can kind of get MATLAB rolling here, I'm going to start with sims. I'm going to define I need m, a, g, and theta of t. Okay. So what is that doing? Well, that's assigning those as symbolic variables, right? And then I can set EQN equal to m times a, which is going to use a assignment equals negative m g times sine of theta. And when you hit enter, undefined mg, right? Because Dr. D got lazy and didn't put the multiplication sign there, right? Because mg is not a single variable. But you can see here what we have, right? We've got a times m, so the acceleration, right, times the mass. Equation of t is equal to negative gm sine theta of t. All right, so that's what we get after we create our linearized model. Well, it's almost linearized, right? But that's our general model, right? For a pendulum with length r, the acceleration of the pendulum bob is equal to the angular acceleration times the radius, right? So we need to put in the radius, sims r, right? And we'll create this equation where this is equal to subs equation, comma, a, comma, r times diff of theta, comma 2. So what is this doing? Well, remember what I just said. For a pendulum with length r, the acceleration of the pendulum bob is equal to the angular acceleration times r, right? So a is equal to r d squared theta dt squared, the second derivative of theta with respect to time. Okay, so make sure that I've got this written out. Okay, believe I do. I'll hit enter, and here we go. We get something that looks like this, right? Where that diff theta of t, comma t, that's our second derivative. Okay, that's our second derivative of theta of t with respect to t. Okay, so what did that do? That just substituted in our acceleration with r times the second derivative of theta with respect to time. Okay, so now what? Well, now we want to isolate the angular acceleration in the equation, right? So we can use the isolate command, right? So we'll have EQN equals isolate of EQN, comma, diff of theta, comma 2. Right, and so all we've done is we've isolated the second derivative, right? Well, what is the second derivative of theta with respect to time? Well, that's the acceleration, right? The acceleration, but why do we want it like that? Why do we want it to look like that? We want it to look like that because we want everything in terms of theta, right? We want everything in terms of theta. If we collect the constants g and r into a single parameter, we can talk about the natural frequency, right? So omega naught is equal to the square root of g over r. That's not something that we need to talk about right now, right? In depth. We'll get into that once we get into time domain and frequency domain responses, but it's something that we can certainly collect, right? So omega underscore 0, right? And equation EQN equal substitute subs EQN comma g over r comma omega sub 0 to the 2. Not sub 0, right, but underscore 0. You know what I'm talking about. Okay. Had an extra en in there, huh? It should be EQN, right? Because that's the function that we're pulling from, right? So again, we're just taking the substitution. We've defined omega naught squared, right? And omega naught squared is going to be replaced by g over r. That's what this is doing, right? And so there we go. We've got diff again of theta t with respect to t is equal to negative omega naught squared sine theta of t. Okay. All right. So that gets us everything we need in terms of our natural frequency and theta, right? And that's great, right? Did you need to do it this way in the lab? No, you didn't need to define the natural frequency, but it's nice to know for when we do things later in the class, right? So now what we want to do is we want to linearize the equation of motion, right? So I am going to define a variable x, right? And we're going to define another variable approx for approximation. And we're going to use the Taylor series sine of x, comma, order 2. Okay. So what is this doing? This is going to take this Taylor series of the sine of x for x to the second order term, right? And we'll talk a little bit more about this in coming weeks, right? And why we want to use Taylor series. Specifically, we'll talk about that when we get into linearization in time domain analyses, right? But suffice it to say, you can use the Taylor series. The other thing you can do is you can use small angle approximation here. If you use small angle approximation, the sine of 0 is what? All right, what's the sine of 0? Leave it in the comments below if you know. Okay, and then we are also going to take approx equals subs, right, because we're going to substitute in 2 approx x comma theta of t. Okay, and this should give us an equation that is an approximation, right? This should give us an approximation term. And notice what it does. It gives us just theta of t, right? Just gives us theta of t. That's pretty awesome. So we can make this linear equation, EQN linear, right? And that's going to equal, substituting in to equation, the sine of theta of t and the approximation. I'm at this one. You need 2 P's. Look, Dr. D has some trouble typing. I apologize. Okay, I'm real sorry about that. But hopefully this will work, right? Cool. So we're left with the second derivative of theta with respect to t, which is equal to negative omega naught squared times theta of t. Okay, this is my linearized equation. What's the difference between this and the non-linearized version? The sign is gone, right? The sign is gone. So that's really nice. So what's step 3? We're going to solve the equation of motion analytically. All right, so I need to set up my sims again. Theta underscore 0 and theta underscore t0. All right. Setting up two new variables. Theta underscore t is equal to the differential of theta. Now I put the semicolon there, right? Semicolon means it's not going to read out. Conditions. Well, given that theta of 0 is equal to theta underscore 0, comma, theta underscore t of 0, which is also equal to theta underscore t0. All right, so we're setting up an array of our conditions. And then we're going to use the assume command, assume that omega of 0 is real. What is this doing? Well, it's assuming that it's real. It's making sure that we don't have an imaginary answer. Why would that be important? Well, that's going to be important later, but not today. Not something we're going to get into today. All right. Next step is we're going to that theta solution of t, and that's equal to dsolve, right? So differential solver, right? We're going to solve the equation linear, EQN linear, by using dsolve, right? And so dsolve is the command, and we're giving it EQN linear, our linear equation, and our initial conditions, right? We don't want to do that. So when theta solve of t comes out, we get theta cosine of omega t, right? Plus theta of t naught times sine of omega t, the whole thing divided by omega naught. Okay. Cool. So let's talk about the physical significance of omega naught, right? The term omega naught of t is called the phase, right? And we're going to get into this in more detail in frequency response, right? But this is the phase. The cosine and sine functions repeat every 2 pi, and the time needed to change omega naught times t by 2 pi is called the period, right? And period is capital T is equal to 2 pi over omega naught, or in this case 2 pi times the square root of r over g, where r is the radius of our pendulum, and g is the gravitational coefficient, right? And so make sure your units match up. If you're using SI, use SI. If not, use English, right? So this brings us up to how to plot our pendulum motion. Now for this particular example, I am going to keep it simple, and I'm going to say that the length of the pendulum is 1 meter, right? And so I'm going to set some things up. I'm going to say, well, G value is equal to 9.81, right? And that's in meters per second squared, right? That's gravitational value. And I will actually go back and spell value correctly because that's how I roll, right? That is, in fact, how I roll, right? So we've got G value. We're also going to have R value, right? And in our case, we said that was 1 meter. Okay. We need omega underscore 0 value, which is just the square root of G value divided by R value. We've got capital T, our period, is equal to 2 times pi. In MATLAB, if you want to use pi, it's just lowercase pi, divided by omega, not omega, omega underscore 0 value. And you can see on the right-hand side in my workspace, all of these things are being defined as we go, right? We also now need to set our initial conditions, right? So let's set those. We've got theta underscore 0 value is equal to 0.1 times pi. Right, and this is the solution is only valid for small angles. Remember, we've linearized this, right? And I talked a little bit about it at the beginning of the video, but we're using the small angle approximation, right? And we've linearized this using a small angle approximation. So the further away that we get from our angle, the more deviation that we have, right? The more deviation we have from the starting angle, the less this is going to work for us, right? The worse our approximation is going to be. And we're also going to have theta underscore t0 value is equal to 0, right? And this is saying that we're initially at rest. Okay. We need to substitute in our physical parameters and the initial conditions for general motion. All right, so I'm going to say vars is equal to omega 0, theta 0. I don't want those to be capital. Theta 0 and theta t0. Oh, t0. Right, so I'm setting up an array with those values equal omega underscore 0 value theta underscore 0 value theta underscore t0 value. Theta SOL solution plot. Well, we're going to substitute into theta solution our variables and our values. Okay, now we're ready. Now we're ready to plot the harmonic pendulum motion. We're going to use fplot. Theta solution plot. Why are we using fplot? Because it's a frequency plot. T, lowercase t times capital T, right? Divided by pi. And we're going to plot it from 0 to 5 seconds. I want grid on. So what did I do? I hit shift enter, right? I want grid on. I want to have a title. Nice. Harmonic pendulum motion. I want my X label. And that's going to be T over T, right? So this is not time, right? This is the ratio of time to period. Y label. Theta pi. Okay. So that has brought up my plot, which you can't see until I bring it over here. Hey, look at that. Well, look. We started at 0.1, right? This is theta divided by pi. It comes up and comes down. It's a harmonic. It's what you would expect, right? The pendulum oscillates, right? Hopefully that's what we would expect, right? That our pendulum would oscillate between 0.1 and minus 0.1, right? And that is the ideal case. But that's probably not what we saw, right? That's not what we saw in our experiments, right? What did we see? Well, we saw the results of a somewhat nonlinear model, right? But before we even get into that, why don't we try something else here, right? Let's try something else. I want us to try plotting like a little movie here, right? So how are we going to do that? Well, I'm going to say x underscore position, POS, is equal to sine of theta, SOLN, or SOL, sorry, sol plot, y underscore POS is equal to negative cosine of theta sol plot f animator at f plot comma x underscore pos comma y underscore pos, right? So we're using f animator. What does f animator do? It makes an animation, right? We're using our previous plot, right? We're using our plot at f plot. That's going to make a frequency plot, right? X underscore position, y underscore position, right? Comma. This is telling us that we want a black circle, right? This is that. We're going to get marker face color as black. K is black. Animation range, and that's going to be 0, 5 times t. Hold on. Right, I'm using shift enter to go hold on. What does hold on do? Hold on tells it to hold what it just did, and we're going to do something else. We're going to put f animator for t. Oops, sorry. Okay, y underscore pos of t, right? We want this to be a line, a dashed line, and that's black. We're going to set our animation range to guess what? Yeah, you guessed it, 0 to 5t. Once you did hold on once, you don't need to do it again. And we're going to do the same type of command, f animator. We're going to have some text. Negative 0.3, comma 0.3, comma timer equal, or timer colon plus num to string, right? So we're going to take a number, turn it into a string, t, comma 2, time, comma 2, plus s. This is the secret sauce, right? Sorry. Animation range, and if you guess it's 0 to 5 times t, well, hey, it's a pretty good guess. So we're going to hit enter. We do all this. What's going to pop up? Hopefully it'll come up in a second. All right, so it still says busy in the bottom corner. We need to wait until it's ready. Okay, just gonna wait for a couple minutes and it should get going. All right, so here it is, right? Here's our animation window, as it were. It's gonna disappear for a second because we need to type play animation. Right, we need to type play animation, and once I do that, I'll pull the window back up. play animation. I'm going to hit enter, and then hopefully you'll see it moving. And look at that. Wow, right? It's pendulum, right? So it's taking our model and it's showing it moving through time. Now it's not super smooth, right? But hey, it gives us an idea, which is pretty awesome, right? We can talk about the nonlinear pendulum model and pendulum motion using constant energy paths, but to be honest, it is a bit outside the scope of this class. So we're not going to talk about it, right? This is a simple pendulum model. We had our timer go for 10 seconds and it worked, right? Now you notice on my screen we had a little mishap here. I put a period instead of a comma. So if you were following this, make sure that you're using this code and this line right here. Okay. Awesome. Well, that'll do it for our pendulum model. All right. Hopefully you guys are feeling pretty good about the lab. Hopefully this helped show you how you can use MATLAB to kind of model that. You could also, right, use the values that you got in your lab and plug them in here, right? So again, comments, questions, concerns, throw them down below, and I'll see you guys in class.